This video is about the behavior of electrons and atomic orbitals. So first let's talk about a continuous spectrum. This is when all wavelengths of visible light are present. So that would mean, because we're talking visible light, that's going to be all the colors of light. And when you put all the colors together, you get white light. And you know this because if you take white light and you put it through a prism, it's going to separate into each of its wavelengths, and you're going to see all of the colors with no gaps, hence continuous spectrum. So let's talk about the Bohr model. And you've seen this and heard about this. We're going to talk about kind of what it looks like in that structure and what happens with electrons. So this part that I'm coloring in the middle, this is the nucleus, and we're not going to talk about this much more than the fact that it's in the middle. Okay, that's where your protons and neutrons are. We want to know what's going on with the electrons. So around the nucleus, we've got these orbits. And we're going to start using the term energy level for orbits. So you've all drawn models like this and seen models like this. Like if you just Google atom and you look at Google Images, you're going to get all these drawings like this. Hopefully they're a little bit better than mine. And then in each energy level are where you're going to have your electrons. So if I draw little dots, I'll see these electrons, right? Okay, so a couple things to note about this. One is that, like I just said, these are your energy levels. And the energy levels, we use the letter N to represent them. So sometimes you'll hear that first one closest to the nucleus is N equals 1. The second one then would be the second energy level, the third, the fourth, etc. So the lowest energy level. So the lowest one is closest to the nucleus. So here's one where you have the lowest energy. And then out here would be the highest energy. So the farther away you get from the nucleus, the more energy that energy level has. So the more energy it's going to take for that electron to be in that position. So electrons can move from energy level up or down. And what we need to know is that when they go up, so they go from like 1 to 2 or 1 to 3 or 2 to 4, anything like that. So when they go out away from the nucleus, they have to absorb energy. And when they go the other way and they go down an energy level, so towards the nucleus, they emit energy. So energy has to be absorbed to go up, right? Because you're going from lower to higher energy, and energy will be emitted or released as you're going down, as you're going from like a 3 to a 1, let's say. So it's important to note, I'm going to draw another little diagram here, that where they start and where they end, they have specific names. So let's kind of like zoom in on like this area right here, okay? And I'm gonna turn it a little bit. So let's say this is my nucleus, okay? And here's my N equals 1, N equals 2, N equals 3. Okay, and if I have this electron, let's say it starts at 1. Where it starts, we call its ground state. Okay, now if this electron is going to jump up to 3, it has to absorb energy. So for this to happen, right, for it to go up to here, we have to add energy. So capital E for energy. So if I add this energy in, and this energy could be in the form of electricity or light, and I'll do a demonstration in class to show this. Okay, if it absorbs it, it's going to go up here, right? It needs to add energy to get higher. Now, it's not going to stay there. That state up there is called its excited state. And at some point it's going to fall back down, and it might fall back down to where it started. It might fall back down to 2, but either way, it's going to fall back down. Let's say it goes all the way back down. And when it does, that energy that was added is now released. And the amount of energy released would give us different waves, different types of waves. If that energy is in that visible light area, you're actually going to see light. Depending on which amount of energy, you're going to see different colors. If it's It could be infrared. It could be ultraviolet. You could actually even get more energy than that. So the amount that's released, we could actually measure and see what it was and how far it fell. So what we're just talking about is where electrons are and how they move around. So with this, we can see this in what we call line spectrums. So you can have an absorption line spectrum or an emission line spectrum. And an absorption line spectrum contains wavelengths. And remember, that's gonna, like if it's visible light, that's gonna be colors that are obviously absorbed. So what you're gonna see here is, you're gonna see, this would be like if we use a prism, you're gonna see different colors, but maybe you're gonna see little gaps where some of them don't exist. Okay, so this is all the color that's absorbed. All right, with those gaps in there. The emission line spectrum is the opposite. This is where your wavelengths that are emitted. So this would be kind of that, whatever's right here and right here and here. And you're only going to see a few distinct lines. All right, so the energy of an atom is what we call quantized. Okay, this means that it can only exist in discrete amounts. This means if it's very specific small chunks. Okay, it can't just be any old amount. There are only certain chunks of amounts that it can come in or be released in. If it wasn't quantized, these emission spectrums that we're actually going to look at in class, they would be continuous. But you will see, or you may have already seen, that they are not continuous. And what you're going to see is you're going to see ones that look like this. We're going to see most of the emission ones. And that's telling us that we have specific amounts of energy that are being released. And these discrete amounts are called photons. All right, so with all of this, when we're talking about light, it has properties of waves, it has properties of particles. So because it can act like both, and electrons act like both, we say that it has wave-particle duality. Which means at times we're going to use waves and those equations to kind of help us determine where electrons are and what they're doing. And at other times we're going to use calculations with things like objects, because it also acts like a particle. So with that, a man named Werner Heisenberg figured out that it was impossible to know both the position and the momentum of an object or particle at the same time. As soon as you kind of are more sure about one, you know less about the other. So when we look at these electrons like a wave, we're actually able to predict where they are or where they will be most of the time. So a man named Schrödinger, who is kind of famous for his cat analogy or experiment, came up with this really complicated wave equation. It's super long, super intense. I won't even show you a picture because it'll just scare you. But that can be helped to determine where an electron is, kind of its orbital region, with about 90% probability. So we're not going to do any of that calculation. That's much higher level chemistry, but we are going to talk about these orbital regions where we're assuming they are a good chunk of the time. So these atomic orbitals, okay, I'm going to come back to this first diagram on the left here, but let's kind of fill this in the middle here. Energy levels or orbits. We just talked about them as being this like N, we use the letter N for them, and they can be 1, 2, 3, 4, 5, 6, and 7. So they're 1 through 7. So those are those energy levels around the nucleus. Within those, though, we have sublevels. So it's within each of those orbits, there's more space, and we can differentiate between the different spaces in them. And those are called our sublevels. And those are labeled S, which is the smallest, P is a little bigger, D is bigger still, and F is the largest. And what we should know about these sublevels is they don't all exist in every energy level, and that they're different shapes. So S are these up here. They're just a sphere. P sublevels are these right here. And P comes in 3 different forms. And if you notice on this P is on the x-axis, this P is on the y-axis, and this P is on the z-axis. So when you put them all together, kind of looks like this cool little flower thing. This is all the P's together. You don't need to know or be able to visualize what a D or an F. They're very complex. I believe there's pictures in the book, but you don't need to worry about that. All right, so now if I go over to this diagram over here, we've got our nucleus right down here, okay? So now think about this with our energy levels, right? We have this first, and I'll do this in yellow. In this first energy level around the nucleus, we have one S. So in the first energy level, the only thing that exists is an S because it's so small, we just have this one sublevel within it. So then in our second energy level, right, and we're going up in energy, we've got 2, right, second energy level, and 2 is a little bigger. So 2 has 2 different sublevels, an S sublevel and a P sublevel. 3 is bigger still, and it has S sublevels, P sublevels, and D sublevels. 4 has S, P, D, and it also, and I'm going to add this, it also has an F sublevel, okay? And all of them after that have all 4, S, P, D, and F. So the orbitals are kind of the spaces within the sublevels. So we're talking energy levels, right? And then we have sublevels within them, and then within the sublevels we have orbitals, okay? So, right, energy levels go down to sublevels go down to orbitals. And what I want you to note is that in an S sublevel, there's only one orbital. That's why all of these S's have this one line. There's only one space inside that S sublevel. P is bigger, right? And it's got these 3 orientations. That's because there's 3 different ways electrons can be in a p orbital. That's why there's 3 lines here for all the p sublevels. So P has 3. D, if you can see, has 5. And F wasn't written out, but F has 7. Okay. And the last thing to note is, and this will come into play more when we get into our electron configurations in our next video, is that 2 electrons can fit in each orbital. So we're able to figure out where the electrons are in terms of the orbital that's within a sublevel, that's within an energy level. And then within that, they can move up and down by adding and emitting energy.